Hey, it's Emma. Let's look at IP addresses in a bit more detail. First, we'll be talking about public and private IP addresses, then network address translation and the related concept, port forwarding, then DHCP, and finally subnets. Routable, also called public IP addresses, are really what we've talked about so far. They're unique worldwide, so if the internet registries are doing their job properly, no two hosts should have the same public IP address. Due to this uniqueness, they can be found by any other computer, including routers, hence routable, as packets can be sent to the public IP address. However, for a local area network, you have a private or non-routable IP address. You can think of public IP addresses as being like full house addresses, which a postman can find and deliver letters to from anywhere. A private IP address is just like the house name, which is specific enough for the local area, but it isn't unique worldwide. Private IP addresses are allocated by network administrators within set ranges, not by internet registries. Using private IP addresses stops using up public ones, though with IP version 6 this is less of a problem. Not every device connected to the internet needs a unique IP address, only the gateway or router it uses to connect to the internet. Network address translation is the way in which public and private IP addresses are linked, and this system is needed so that devices with private IP addresses can be given access to the internet. So when a host with a private IP address wants to send a packet that can be routable, the private IP address needs to be replaced with a public one, especially if a message needs to be returned. Remember, the packet header contains the IP address of both the sending and receivable device. When the router receives the packet, it replaces the private IP address with its own public one and replaces the port number of the application that initiated the request with a port number it generates and reserves for this transmission. For a short time, though, it will eventually expire. In a translation table in the router's database, it will associate the port number it generated with the original private IP address and the original port number. When an incoming packet to the router from the internet has the port number 2000, in this example, it will look up the private details, swap its details in the packet for the original hosts, and send the packet onwards to it. NAT has helped ease the transition to IP version 6, as it helps minimize the number of public IP addresses. Port forwarding is like a special case of network address translation. It's simply a method of routing data using additional ports and is commonly used when a server with a private IP address is connected to clients on the internet. For example, port 80 is used for web requests. So when a client on the internet wants to access the web server, it will use port 80 and the router's IP address, and using the actual private IP address of the server won't work. The router can be programmed to recognize and forward the packets on with the port number of 80. IP addresses can be configured either statically or dynamically. Static IP addresses are ones which never change once assigned to the host. Dynamic ones are assigned every time the host connects to the network, managed by an application using the Dynamic Host Configuration Protocol and through DHCP servers. A DHCP server is a dedicated server, perhaps run by your ISP, that manages the pool of available IP addresses and allocates one to a host every time they connect. It will then remove it from the available pool until the client connects again and logs off the network. It's more complicated, but it's a more effective method than using static IP addresses, especially when you're dealing with a finite number of available IP addresses, though this will be less of a problem when IP version 6 is fully introduced. IP addresses are split into two parts. The first bits, from the left, are for identifying the network, and the last bits are for identifying the host, or the device, connected to that network. The size of the host ID is determined by how much space the network ID takes up. When the network ID is written on its own, sometimes the parts where the host ID would be are written as zeros, like this example here. Subnetting is the process of creating smaller networks within one broader IP network. For example, a network administrator might want to split the building's IP addresses into one for each network on each floor. This would make it more manageable and reduce the load of network infrastructure. We've talked about this with data collisions before. It also allows you to isolate certain hardware, like printers, and if organized properly, means data only goes where it needs to, not around the entire network. IP addresses are split into these two components so that subnetting is possible. When one host on one subnet sends data, it will first check the network ID of part of the destination IP address to determine if the destination device is on the same subnet. If it is on the same subnet, then the network ID of the IP address will be the same as its own. This is done using a subnet mask. The best way to look at subnet masks is to convert the IP address from decimal to binary and take it from there. Say this IP address in both decimal and binary form is for a host on a subnet. Also, let's say that the first 3 blocks are for the network ID, and the final block, the 5 in decimal, is for the host ID. A subnet mask is just a string of binary numbers that's generated so that the entire network's ID are part of are ones, and the host ID parts are zeros. Every device on a subnet will be programmed with this subnet mask. Masks are just there to be used in calculations in order to omit parts of a binary number, in this case to remove the host ID part. The operation that does this is bitwise AND. If you haven't done this before, you basically just multiply each number by the one below it and write the result. So starting from the far left, 1 times 1 is 1, 0 times 1 is 0, etc. The result is you just get the network ID. Remember that I said you sometimes write in the ones to signal where the host ID would be. The same operation would be carried out on the destination IP address, and if the results of both are the same, i.e. if they both have the same network ID, then data does not have to be sent outside the subnet. It can go directly from sender to receiver. This process does seem overly complicated from a human perspective, but of course you have to bear in mind how specifically computers need to be programmed. Okay, well, let's recap. So, we started by saying public IP addresses are uniquely worldwide and will be used by routers across the internet. You can also have private IP addresses, which are not routable and only have to be unique within their own network. Network address translation is when a router translates between public and private IP addresses, so a device with a private IP address can send and receive data from another device with a public IP address. Port forwarding is like a subset of this, but it involves the router being programmed with a set port for the server it is to be forward dated to. Dynamic host configuration protocol servers assign dynamic IP addresses to hosts when they connect to the network from their pool of available addresses. IP addresses are split into an ID for the network and an ID for the specific host. Neither have a fixed size. Using this property, you can subnet, i.e., create smaller networks within a larger one, because you can check the network ID to determine whether you are on the same network. This means you don't have to route data unnecessarily. A subnet mask is used to get the network ID only, with zeros as placeholders for the host ID part, so you can do comparisons to see if you're on the same subnetwork. A subnet mask is just making the network ID parts all ones and the network host ID parts all zeros. Then they use the bitwise AND operation with the mask and the IP address.